Hello, my name is Emre. Today we will present our project Speech Denoising with Deep Learning. So in short, we built a pipeline that takes live microphone audio, removes noise using a lightweight deep learning model, and outputs enhanced speech in real time. The three key pieces are a CNN-based denoiser, an ideal right ratio mask target, and a real-time MATLAB pipeline. So the challenge is that real-world noise is often non-stationary, so it changes over time. Traditional DSP methods can work well for stationary noise like constant hum, but they struggle with unpredictable environments like crowd chatter, traffic, or keyboard clicks. So our goal is to separate clean speech from noisy mixtures while keeping speech natural and intelligible. So you can see in the waveforms and spectrograms how noise can mask speech, structure, and harmonics. So as we proceed, you can see that our approach is informed by prior work in deep noise suppression. Benchmarks like the Interspeech DNS challenge show deep learning can outperform classical DSP with large datasets and evaluation frameworks. So architecturally, there are two directions in the literature. So the models that capture temporal dependencies and phase-aware enhancement methods. So we use these insights, but we focused on a practical design that we can actually run in real time with low latency. So here is our end-to-end blueprint. We start with 48 kHz audio input, then pre-processing downsamples and buffers the signal for SDFT. Next, the CNN performs inference to estimate an IRM mask for the noisy spectrogram. Then post-processing applies smoothing and reconstructs the signal via inverse SDFT. Finally, we output audio again at 48 kHz for playback. So the key idea is we do heavy learning on a compact representation, but we keep the full streaming system stable with careful buffering and resamplings. So as you can see on this slide, to make the model more robust, we created a custom dataset, including speech sources, noise sources, and the mixture of them. So we got the speech sources from Turkish speech from Mozilla Common Voice and the noises from ESC50 environmental sounds, which are diverse and non-stationary, like 2000 noises on there. So for mixture, we mixed clean speech and noise at different SNR levels using a gain factor to cover both slightly and heavily corrupted audio, creating a diverse mixture. So this gave us control to realistic noise inputs, so the model learns noise suppression without losing speech content. Now Bart will explain a key turning point in model design, the CNN architecture, and how we made it run in real time.
Experiments, we tried direct spectral mapping, training the network to predict the clean spectrogram directly from the noisy one. It reduced noise, but speech often sounded metallic and unnatural, what we call the robotic voice. The reason is oversuppression. When you minimize MSE aggressively, the model can learn to mute frequency bins too strongly, creating spectral holes that destroy the natural timbre. So the big lesson here is low numerical error doesn't guarantee good perceived audio quality. To fix that, we changed the learning target to the ideal ratio mask, IRM. The IRM is the ratio of clipping magnitude to noisy magnitude, clipped between 0 and 1. The network predicts this mask for each time frequency bin. Then we multiply the noisy magnitude by the predicted mask to obtain an enhanced spectrogram. Why is this better? First, it's a bounded target, which stabilizes training. Second, it preserves naturalness because instead of inventing a spectrogram from scratch, we attenuate noise while keeping speech structure. This slide shows our lightweighted dilated CNN. The input is a time frequency patch, and we use dilated convolutions to expand the receptive field without dramatically increasing parameters. That helps the model capture broader spectral context efficiently. We use leaky ReLU activations to avoid dead neurons and keep gradients flowing, and the sigmoid output to ensure mask values stay in the valid 0-1 range. Training is done with Adam and an MSE style loss for the mask prediction task. Making the model work in real time required engineering beyond the network. First, there's a sample rate mismatch. Many audio devices use 48 kHz, while our model runs at 16 kHz. We handle this with downsampling before processing and unsampling after reconstruction. Second, we need stable streaming. The STFT hop size and the audio device frame size differ, so we use a ring buffer to avoid gaps and keep a continuous data stream. Third, the system integration. We can route enhanced audio through a virtual audio cable so it can behave like a microphone input in apps such as Discord or Teams. Even with a good mask, raw network outputs can fluctuate from a frame to frame, producing watery artifacts. We added attack release smoothing. Quick attack so it responds fast and slow release to preserve natural tails of words. We also add mask flooring, a minimum mask value, so the output doesn't become unnaturally silent. This keeps a small, consistent ambience and reduces the dead silence effect. Now Eray will show the evidence what we learned from the metrics like RMSE, alternative approaches we evaluated, and our final conclusions and future directions.
Here we show qualitative evidence, waveform and spectrogram comparisons. In the noisy input, the noise floor is high and speech harmonics are partially obscured. In the enhanced output, the noise floor is noticeably suppressed while harmonic structures are clearer and temporal smearing is reduced. This is important because good denoising isn't just removing energy, it's preserving the speech patterns that the ear uses for intelligibility. A crucial finding came from hyperparameter tuning. If we push training to get the lowest RMSE, the model can become over-aggressive, producing over-suppressed audio that sound robotic or muffled. The best model was in a sweet spot where RMSA converged to a stable, moderate level rather than the absolute minimum. So the conclusion is perceptual quality is paramount. Objective losses guide training, but they must be balanced with the listening test and perceptual metrics. We also evaluate alternatives. One option was a time domain BLSTM or encoder-decoder style mapping. Um, these approaches can be very slow to train due to long sequences, and they didn't consistently beat our frequency domain mask approach in perceived quality. Other direct mapping approaches were also more prone to robotic artifacts. In practice, our mask-based CNN provided the best trade-off between performance, stability, and complexity. To wrap up, we successfully built a real-time speech enhancement system in MATLAB. The IRM-based dilated CNN offered a strong balance between noise reduction and natural speech. The end-to-end pipeline handled 48 kHz input-output, 16 kHz model processing, buffering, and post-processing for stable streaming. For future direction, we can reduce latency further with the causal convolutions and shorter context windows, improve temporal consistency with recurrent layers or streaming transformers, and enhance fidelity by incorporating phase estimation or complex valued masking. Finally, these are key technical settings and evaluation ideas. STFT parameters, training hypermeters, and recommended objective metrics such as STOI for intelligibility and fuel QA for perceptual quality, along with distortion measures like SI, STR, and segmental SNR. At this stage, we will first test the non-live test code. When we start the program, it asks us whether to use a pre-made noisy sound file or generate a random noisy sound. We will click on this option. Then we find the generated noisy sound and the clean sound here.
Kendi içerisinde farklılıklar barındırmaz. Kendi içerisinde farklılıklar barındırmaz.
We can say that it suppresses the noise really well. Now we will run the live test code. Here we use the virtual VB audio program to make the computer see the sound we process into MATLAB as if it were a microphone. We see the instantaneous delay here. We turn off the sound enhancement in Windows settings so that there can be a fair comparison. Voice 1, 2, 3.
Voice 1, 2, 3.
Okay. Second one. Voice 1, 2, 3.
Voice 1, 2, 3.